Welcome everybody again for the second lecture of the course of mirror symmetry by Alex Cruz Morales from National University of Colombia. So, please.
So thanks, Marina, for the introduction. So we will, this time actually we will discuss mirror symmetry for quantum manifold. Last time I gave a wide overview about mirror symmetry, particularly for Calabi-Yau manifolds. But the main topic of this lecture is mirror symmetry for quantum manifolds. So today I want to discuss some picture about this. Again, I mean, the picture will be incomplete and biased. It's actually my own picture of mirror symmetry. I mean, based on the work of many people, and there are other approaches to mirror symmetry for phonons, but the one we actually need for the other lectures is the one I want to discuss today. So let me start saying what a Fanon manifold is. So Fanon manifold is a smooth, complex polarity X such that its anticanonical line bundle, which is actually minus kx, which is the determinant of the tangent, is ample. Okay, other way to see this is like the Fertian class is positive, right? In the Calabi-Yau situation, we were in the Fertian class equal to zero situation. Now we are in the positive situation, right? So in dimension one, in dimension of x is one. So the only Fano manifold we have is the projective space. So x is the projected line. So it's equal. So I'm consider only varieties over the complex numbers. So that's what when I talk about the the projective space. So I am talking about the complex projective space, right? I mean, all the varieties are complex varieties, right? So if the dimension is two, so there is a classification of this. So x is the so-called del peso surface. Actually, it's one of these. Is P2, P1 times P1, or is the blow up of P2, the blow up of P2 in at most 8 points in general position, right? So that's actually it's actually in generic position. Right? So in fact, one interesting example is if you consider the blow up in 4 points, P2, because this is actually by some result by Kapranov. This is in fact the compactification of the moduli space of Gino zero curves with 5 mark points. And this is really interesting because I guess in the next week, in the lecture 3 and 4, I will actually discuss this situation in more detail because the mirror symmetry of this Fano manifold, this is actually this is non-toric. That's interesting because it's the blow up in 4 points, so we get a non-toric Fano surface, but del peso surface. So, and the interesting thing is like, somehow the mirror symmetry of this thing, the mirror symmetry of M0 5 band, which is also the del peso dp phi, it's also known as del peso of degree phi, is actually related to the Aperi proof of the rationality of theta 2. Of course, I mean, the rationality of theta 2 was known from Euler times because theta 2 is equal to p squared over 6. But there is this work by Aperi, when actually he proved the rationality of theta 3 and also theta 2. And the rationality of theta 2 is related with the geometry of this, and in fact, the mirror symmetry of this double pressure surface. And this is really an interesting, part of mathematics. This is a very nice piece of mathematics here. So I hope I will discuss this in the next time when I discuss about the mutations, and in the fourth lecture when I discuss about the exponential periods and some kind of more number theoretic things related with mirror symmetry. Good. Okay. So let's go in that for dimension 3. So if dimension of X is 3, so there is a classification also. So Fano treefolds are classified. Fano treefolds are classified. So there is this classification by Skopsky. Okay. He actually classified the Fano manifolds when the Picard mean is the integers. So the Picard rank 1 situation. Okay. So there is there 17 families here. And the full classification is done by Mori and Mukai. Actually, Mori won the first medal in part of for this work. This is in general. And at the end, we have 105 families for final trifolds, right? So the classification problem for higher dimensions, higher than 3, is still an open problem. This is a very interesting problem, actually, in algebraic geometry. So for higher dimensions, and higher means higher than 3, the classification problem is open. It's open. It's very interesting problem. And in fact, there is a program, and I will discuss a little bit more about this later today. There is a program called Fano. Sorry, I don't know what happened. Okay. This program called Fano Search program by Kotz, Korti, Galkin, Golichev, and Kaschik. Okay, and the programmers try to use they try to use mirror symmetry to classify the Fano manifolds. So they want to study this problem of classification of the Fano higher dimensional Fano using mirror symmetry. So I will actually back to the idea of this program later. So just for the moment, just let me mention that there is this application of mirror symmetry in this problem, which is purely algebraic geometry problem, the problem of classifications, right? And for us for today and for talks, so the important examples we have for Fano in any dimension are given by the projective spaces and also you want Riemannians and find complete intersections in projective spaces and this kind of thing. So actually, for today, you want to use consider the projective spaces will be enough. That's completely fine in order to understand. I mean, conceptually, what I want to discuss, right? Perfect. So that's the final that's the final manifold. That some examples. So let me just ask, okay, what is the mirror of a final manifold? What is the mirror of a final manifold? X, right? So I will use the approach by Katsarkov, Kontsevich, and Pantev to answer this question. That is actually answered by one of the first answers was given by Giventhal from the mathematical point of view, by Horia Baffa from the point of view of physics. But there's actually this is kind of summarizing this in some paper by Katsak, and Pantev. So that's the approach I want to present today. So you will have X is a final manifold, so it's final manifold, right? We have omega X, its complexified color form, complexified color form, right? And SX is the anticanonical section, anticanonical section of X. Good, okay? So we claim that the mirror of this trap is this tuple. So the mirror of X with this complexified color form on this anticanonical section is the following tuple. Is the tuple. Here we have an object y w omega y and ball y. And I will say what these things are. Where so this YW is what is called holomorphic Landau-Ginzburg model. What is actually a holomorphic Landau-Ginzburg model? So it is used. Y is a quasi-project Calabi-Yau manifold. Calabi-Yau manifold. Okay, the dimension of Y is equal to the dimension of X. It's actually the complex dimension, right? So we're calling this N. The complex dimension is N. And is W is a function from Y to the complex numbers, okay? And this is an surjective algebraic function. And we call this potential function, potential. And some people actually also call it superpotential. So you find in the literature potential or superpotential should be somehow the same. With this condition, with um, the critical locus is compact actually. With compact critical locus. Critical locus is okay. That's good. That will be the the mirror. So I will say what actually means that these two things are mirror in a second, but just let me say some remarks. Okay, maybe I have to also to say which who is omega y is a complexified color form. So complexified color form on y, and this volume ball y is holomorphic volume form. Volume form on y. This holomorphic volume form will play a very important role in the next lecture actually. Volume form y. Okay. That's the mirrors. So usually we just forget about omega x, sx, and omega y both y, and we just call x and the Landau-Ginzburg model mirror to each other, right? So usually we just forget this. Things I will only we talk about x and the Landau-Ginzburg uh, model, right? These Landau-Ginzburg models are what we call last time geometry with potential. So this Landau-Ginzburg model, LG model, Y, and W is what we call geometry potential. Okay, so last time we actually mentioned a little bit about this. So let me make some couple of remarks before going to compute an example. So the first remark is like the anticanonical section, the anticanonical section is X. So actually defines a Calabi-Yau hypersurface in X. Defines a Calabi-Yau Calabi-Yau hypersurface dx in X. So okay. So if we require that dx is smooth, this is actually uh, requiring the potential to be proper. So requiring that this hypersurface is smooth, which is mirrored by the requirement that W is proper. It's a proper one. Right? And it will require that this dx actually has a strict normal crossing. So this actually is mirrored to ask to the fibers to be some Zariski open subsets in n-1 dimensional Calabi-Yau manifold. So requiring the dx, this hypersurface, has a strict normal crossing. Okay, it's mirrored by the requirement that the fibers of W are Zariski open subsets in projective n minus one dimensional Calabi-Yau manifolds. One-dimensional Calabi-Yau manifolds. So, so that's what you actually, see. You can see it, as some people ask, to the potential to be proper, so or that the fiber has this, uh, they are related with this n minus one dimensional Calabi-Yau. So that means that you put some, condition on the hypersurface defined by the canonical section. So I just mentioned this, but I guess in the picture I tried to describe today, they don't actually play a very important role. So what are the best, way to understand what is going on here with the mirror? Fun probably is looking at examples, and maybe one of the good examples to look at is the mirror of projective spaces. So let's try to discuss a little bit the mirror of projective spaces, which will be kind of a nice example to understand what is going on. So the mirror, there's a question, sorry, Alejandro.
Oh, no, no, sorry. I thought I had this muted.
Okay, so no problem. Okay, mirror of projective spaces. Okay, that actually comes from this Horibafa story and also given title picture, right? And then, in fact, what I want you to see is how to interpret this Horibafa and Evental in terms of some nice combinatorial object, right? And this the thing, right? So let's see what is we have in the middle. So we have X, complex projective space, Pn, right? This is the projective space. Okay, let's call it as X0 on to X, probably not X. I have here my mouse view. Let me use the same notation in order to avoid confusion. So UN, this is at the homogeneous coordinates. Homogeneous coordinates. Okay. This omega X is just the Fubini study form. Fubini study form. And the X will be just the union of the n minus one coordinates hyperplanes. So remember that this dx is actually somehow equivalent to work with the sx, because this is the the hypersurface we get from the canonical section, right? Yeah. Okay, good. So what we have on the mirror side? So on the mirror side, we have the following. Okay. Something happened here. Okay. On the mirror side, we have so y will be the n-dimensional torus, right? N-dimensional affine torus with coordinates z1 to zn. Right? So the potential W will be the function from the torus, and dimensional torus, to the complex number given by, so W of zeta 1, z0, z1, zn equal to the sum of ci I1 to n plus 1 over the product of these coordinates. That will be the mirror. So the omega y will be this form, 1 over to the value of c squared zi, which is zi bar, and the volume is just the standard volume form. The standard volume form.
Excuse me, Alex. In the previous formula for the double view, how did you do to not get a zero there? Is this zeta I minus zeta n in the denominator there?
No, okay. Here is done. Here is the product.
It's a product.
It's a
Okay.
product. Sorry, yeah, it's a product. It's zeta 1 times zeta 2 times to zeta n. It's the product of
Of
all of
all the
them. Yeah,
zetas.
sorry.
Okay. Thank you.
Yeah, exactly. Okay, yeah, it was yeah. Actually, my handwriting was quite bad. But yeah,
Okay.
it's the product. In fact, one observation is that we get our own polynomial. So I will do it in in a moment. But yeah, what we get is our own polynomial.
Okay.
Good.
Thank
So
you.
let me just say exactly. Let me just say something. So this is not really this is somehow the usual thing. So you want to consider not the toric divisor, but a smooth Calabi-Yau hypersurface. So we need to get not this y, but a partial compactification of y in order to get a proper Landau-Ginzburg, sorry, a proper map. And then we have to extend the volume form and the omega y as in order to I mean we need to extend to that compactification, right? But that we don't I don't want to discuss that, but that's something we can do, for example, to if we consider not the toric device of CPN. But there is, these two main questions. So two main questions. So in which sense, first, in which sense this Landau-Ginzburg model we use construct this C times N with this W is mirrored to CPN, the complex to the projective space. And the other thing is, like, you see, this W is actually a Laurent polynomial. So W is a Laurent polynomial. So how general is it? How general is this? So what I want to say how general is, okay. So if you have a Landau-Ginzburg model mirrored to Sonfano, when we know that this is a Laurent polynomial, or if you want also to ask the other way around, if you have a Laurent polynomial, how do you know if it's the mirror of Fano or not? Or you also want, okay, it is possible to understand the mirror of the Fanos use restricted to Laurent polynomials and not more general Landau-Ginzburg models. That will be like this second question, right? So I will actually discuss this two questions and say, okay, what will be the answer for for the one, which is actually not only the answer for one, but the answer for general fanos, or at least for certain type of fanos. And actually, the answer for the certain type of fanos is related with the second question. So to see which cases we can just consider just Laurent polynomials, and everything can be just reduced to Laurent polynomials, right? So let me just discuss this first question, and I will for the first question. So let's discuss this for the first question. So for this thing, I will use the approach by Coates, Corti, the people in the Fano source. Coates, Corti, Galkin, Golichev, and Stin. Let me just and then actually this approach here, we will see that it will be kind of related with or will be actually this Hodge theoretic approach to mirror symmetry. But let's discuss a little bit. So let me first start in defining what is the classical period for a Laurent polynomial. So classical period for Laurent polynomial. The classical period for Laurent polynomial. Okay. So just consider a Laurent polynomial. So let W be function, right? Laurent polynomial. What does it mean? So in n variables. So this means that actually W belongs to this ring, the ring of Laurent polynomials. Yes, sorry, this is mistake. One, this is x2. So previously I used the z variables, and now I using the x variables. So these x1, x2, xn are the z1, z2, zm before, right? Sorry. So this use. I mean, I hope there is no confusion with the notation, but these x1, x2, xn are the z1, z2, zm before, right? Okay. So there's these x1, x2, xn are the standard coordinates in the torus, right? Perfect. So what's the classical period? So the classical period is the following integral. We call it this pi w t, the variable t, this integral 1/2 pi I, and this I is the square root of -1. I will integrate over this cycle x1 equal to x2 equal to xn to 1, and we integrate this thing 1/1 minus t w in these variables, and the usual 4. This is the so this is the volume form. Okay, that's the classical period. This integral. So I want this I want to discuss how the way to construct the period, that there's a way, a combinatorial way to get this thing, which is really important, but you can find it, for example, in the paper by Coates, Corti, and collaborators, right? So the important thing, one of the important facts is this following theorem. And the proponent said that this classical period, so PWT, actually satisfies an ordinary differential equation. Ordinary differential equations for the E. Okay. Let's call it L. So we have this equation is L equal to 0, and this L is just an differential operator. So this L is just a differential operator. So kind of differential polynomial. It's a differential polynomial. It's a polynomial differential operator. And this D is T ddt is this, right? So this is remark. In fact, this operator L is a Picard-Fuchs, or what this is what is expected. This is a Picard-Fuchs operator. It should be Picard-Fuchs. So let's do it an example, right? Of this operator. Let's do an example of this. So an example. So let's consider the following around polynomial. So we have L, the W, and we have this W in two variables, X and Y. And is this Laurent polynomial is X plus Y plus 1xy. So you follow actually what we discussed before. So you go to this W here at the end. So you see that it will be the mirror of CP2. And we will show that it is in fact the mirror of CP2. Right? But let's wait for the discussion. So we have this Laurent polynomial. So we can compute the period, and the period actually in this case is this series. This series factorial and factorial U T Gm in this period. So the coefficient of this series, so the coefficient satisfies the coefficients satisfy the following recursion formula, the recursion relation m squared c3m minus 3 n minus 1 3n minus 2 c3m minus 3. This is m here. And this is actually comes from doing some combinatories with the Laurent polynomial. And actually this is equivalent to say that the period actually satisfies the following differential equation: d squared minus 27 t cubed d plus 1 d plus 2, right? So this equation. So this guy here is the L. So this is the operator. So let me just write here
Alex,
in the page.
just
Yeah,
may I interrupt with a
sure,
crazy question? You mentioned
sure.
something about a proof of the irrationality of zeta 2. I mean, I now see this PW, I mean, your pi, your function pi, it looks like a
Exactly,
series
exactly.
that.
This is exactly. This will be in the case of the operator, it will be the series given by the operator. Exactly.
I see, okay.
Exactly. That what I plan to discuss next week, but you're right. Exactly. We don't consider the CP2, but the DP4, DP5 example. then the classical period should produce this. I mean, we can produce, as a the classical period, we can produce the Aperi series, right? That's true.
Okay,
It's
thank you.
exactly the thing.
So
Thanks,
I
Maria,
was
because
guessing
I
that.
have to say I have to say something. Thank you, thank you. You remember something that is important. Let me back to the beginning, to the three folds, right? Sorry, I forgot to say that this is very important. It's related actually with this, with actually Marina question in some sense. You know, we are in three folds. There is this particular three-fold B12, right? And the mirror of B12 of this is related actually to the rationality of theta 3. That's the thing.
I see.
Very important. And again, if you compute the classical period of the mirror of these things, so we get the rationality of theta 3. And then actually that was important because, you know, the Aperi proof was really, really mysterious. And people like Boykers, Striensta, other people try to understand somehow what will be the geometry behind that. And somehow today we can say, that, okay, the geometry of these things is actually closely related with mirror symmetry. And you can ask, okay, what happened with zeta 5 and zeta 7, and they are open, right? So we don't know. It seems there is no final approach to this thing. It seems zeta 2 and zeta 3 are really quite special, but we don't know why. Maybe the keys should be the mirror symmetry of these things. So thanks for, you know, because I forgot to make this remark that the zeta 3 also appears in the mirror symmetry of Fano. And so Marine actually pointed out we need to consider now the periods for this B12. Maybe I can also try to do something about B12. It's a little bit more complicated, but maybe I can say something next week. Good. So let me just write again the operator because we will get this operator in a moment. Again, so d squared minus 27 d cubed d plus 1 d plus 2. Okay, that's the operator. Good. Is that the story from the side of the Landau-Ginzburg models, right? So let's go to the Calabi-Yau, sorry, to the final manifold. So let's define the quantum period of a final manifold. So from the side of Landau-Ginzburg models, we get this classical period and the corresponding differential equation satisfied by the period. And now what we want to do is from the final side, we also want to get some kind of period, some kind of integral you want, and then to see that this is actually this satisfies certain differential equation, right? Then let's do this. But for the moment, let me just be a little bit more general because I want to define some kind of Gromov-Witten invariance, and this definition I will make is more general. So it applies for more general varieties, not just for quantum varieties. So let me start with a big, more general picture. So let me start with just a smooth projective variety over C. So X is just a smooth projective variety over C, right? You take some class in H2. And I will use actually the notations in Galkin, Golichev, and sorry, Galkin, Kotz, Corti, Kashik paper. So there's not kind of a standard notation, but I will use that notation. So let me use this X, 0, 1, beta to be the model space of degree beta, stable maps to X from genus 0, corpse with one mark point. Okay. And you just consider this the virtual fundamental class. Well, I just said this just to fix the discussion, the notation, maybe somehow the details. I don't want to make details so because we actually need probably use one course just to define what a virtual fundamental class is. But this is something that actually we need to define in order we want to define the Gromov-Witten invariance properly. So we really need to consider these spaces, these model spaces for stable curves, and we actually need to define what the virtual fundamental class is. Okay, this is the virtual fundamental class of this space. Perfect. Okay. So the other thing I need the evaluation map on this model space to X. This is the evaluation map at the map point. Okay. We need another thing. Thing is C is just the Fertian class or the universal cotangent line at the mark point. So coefficient. This is the first Chern class of the universal cotangent line at the mark point. With all of these things, so we can define the following thing. Actually, this is defined by Giventhal. So this the so-called J function. So the J function, you want the Giventhal J function, X, right? It's a generating function of the Gromov-Witten invariance. So generating function for gene zero Gromov-Witten invariance. This gene function has the following very, involved formula: sigma plus tau into E sigma Z E tau Z times 1 plus, I will write the sum here because I probably don't have a space there. So the sum is over the beta classes, beta equal to 0, q beta E, so this pairing, rho and tau, and let's pull back of the evaluation one. It is the virtual fundamental class intersecting with this extension of this class, right? So who are these things? So this sigma is an element in H0 of X Q. This tau is an element in H2, right? This Q beta is the representative of beta of beta in the group ring Q H2 X C in this group, and we expand this fraction z minus psi as the series z minus k minus 2 okay, so, right, this is a little bit really kind of involved. I mean, there is a lot of things we have to define just to give you the idea what is the j function, but we are in the final case we can do it easy, so in an easier way. So if so let's consider X final manifold, right? So we'll use what you consider one component of the J function. So consider the component of the J function, Gx sigma plus tau along the unit course. What does it mean actually? So we just can set this sigma tau used to be 0, z to be 1, right? And we can replace this expression by this expression with this, how the canonical pair here. Okay, x. Okay. So in fact, this if we do that, this formula for the j function can be used expressed in these terms. So gx can be expressed as the following series. So I will change a little bit the notation. So we say the g x t, right? 1 plus e equal or bigger than 2. And this sum here also over the betas h2 xc beta, and this pairing is equal to d, and the expression in this sum is td 5 ball c minus 2 x 0 1 beta, and this expression here is just Gromov-Witten invariance, and certain Gromov-Witten invariance, yes, and so certain Gromov-Witten invariance. Right, so this phi ball here is just the top degree cohomology class on X, such that when you take the integral of this over X is equal to 1. Okay, so we get this expression, and so this gxt is called the quantum period of X. So let me just summarize the thing. So what is the quantum period? So you have the Gromov-Witten invariance. So you define the J function, which is the generated function of the Gromov-Witten invariance. So you take you take the component along one direction, along the direction of the unit class, and expressing this as this series. So that's what is the quantum. What is the quantum period? So the quantum period is a kind of certain, generated function for the Gromov-Witten, or certain type of Gromov with an invariance, right? So we can write this complicated series. let's write this as this series. So gx t equal to 1 plus the So you can say, okay, so maybe you are asking yourself, okay, what is the relationship between the quantum period and the classical period for the Landau-Ginzburg model or the Laurent polynomial I defined before. There is an interesting thing here, actually. So somehow the J function is a solution, so it's a differential equation, but remember that when I talk about the Laurent polynomial, I said that the equation is Picard-Fuchs. This means that actually the singularities of the differential equation are only regular singularities. However, here, the differential equation I am getting is not a differential equation with only regular singularities. It's a kind of different differential equation. It's a differential equation with two regular points, one at 0 and infinity. At 0 or at infinity, it doesn't matter. It depends on which local coordinate you use. So let me just say that at 0 is regular, and at infinity is irregular. It's a pole of order 2, right? So it's not a Picard-Fuchs, right? So we said, okay, how this actually could be related to the other equation, but we cannot make some procedure what is called regularization. What is the regularization? Essentially, you take the Fourier Laplace transform and make some reduction, so you get a differential equation only with regular singularities, and you get the corresponding solution, which is the regularized quantum period. So we using the Fourier Laplace transform plus some, this reduction is just to take out some common factors in the differential polynomial, and then to get out these factors, these common factors. So we get the equation we want, and the corresponding solution is the regularized quantum period, right? So we can do this thing, but in fact, okay, so the regularized quantum period of x is this gx hat at the level of the series. Is almost the same series we had before, ZD, TD, but a factor here appears, this D factorial. That's the difference, right? And how this thing works at the level of differential equations. So again, so the quantum period, let me probably write that, quantum period satisfies an ODE, which is not Picard-Fuchs, right? And then, and the regularized quantum period satisfies an ODE obtained from the previous one the Fourier Laplace transform plus some reduction. This procedure is called regularization. Let me just say that in fact we can consider not just this regularization, and what we get on instead of the classical period, we should get some oscillatory integrals. That's the Giventhal original picture. And actually, it will play an important role in the story I will discuss in lecture 4. In lecture 4, I want to discuss exponential periods, which are not, so these classical periods are periods in the usual sense of periods. I will define that in the fourth lecture. But there is also this extension of the periods actually proposed by Concevich and Seguier and developed by Javier Fresan and Peter Johnson. And we can actually tell this story in terms of the exponential periods. And somehow I'm quite more interested in the exponential period side, and we will see why. But for now, for today, I want to use the regularized version, right? Because you see, it is quite in certain sense close to the picture I described for the Calabi-Yau situations the first time, right? Let's go to the example of CP2. So let's do the projected plane. So, okay. And this is the cohomology ring. Okay. And this P is actually the hyperped class if you want, right? This is the class. So you choose a basis here, choose a basis. So this this is 3 times this class and keep the k square is 1. So this is a basis for cohomology. So you didn't say that, but this gamma weight and invariance, this information coming from the J function can be packaged in what is called the quantum cohomology ring. So this is the quantum cohomology ring is in fact a deformation of this is the cohomology ring by the structural constants given by the Gromov-Witten invariance, and using the quantum product we can produce the quantum differential equation, so which is the differential equation satisfied by the quantum period. So this differential equation satisfied by the quantum period, we call it the quantum differential equation. So, and we can get it from the information of the Gromov-Witten invariance. So choosing a basis here, we can get the quantum cohomology ring, and then we can get the quantum differential equation. So in this case, so the quantum differential equation for CP2, so the quantum differential equation, so we use to compute actually the quantum product by the anticanonical class. So let me call it QX is just this D3 minus 27 D3. Okay. And the GT, the period GXT, which is D3. Right. So this equation is the regular type of equation. So we need to take the Fourier Laplace transform. Here is the formal Fourier Laplace transform, right? You change the dt dt by minus t and the t by dt dt. So you make this formal algebraic Fourier Laplace transform here from this operator, and then take out the common factor, right? And then after the regularization, we get after the regularization we obtain the following. So the differential equation, we call it hat. The operator is d squared minus 27 d plus 1 d minus 2. And the period will be, you get the she hat will be the corresponding classical period. So this is actually L. This is the L before we get from the classical period. So that's what we mean by a Laurent polynomial is mirror to the finite manifold. So mirror symmetry here means that you get the quantum period, the regularized quantum period, sorry, from the point of view of the Fano, you get the classical period from the point of view of the Landau-Ginzburg, the Laurent polynomial, and then these two periods match. That's mirror symmetry. And that's the Hoche theoretic somehow mirror symmetry. You remember when I talk about the case of Candelas de la Osa, Green and Park's computation? So as you compute, the number of rational curves for the quintic, and this counting of rational curves, I said that is related with the Gromov-Witten. So they went to the B model, compute some periods, use the mirror map, to get the number of rational curves in the original problem. This is something what is happening here, right? So that's what we call it, the Hodge theoretic mirror symmetry for fans, right? So this is the Hodge theoretic mirror symmetry, and it's the picture we will use next week and actually during this lecture somehow. So Laurent polynomial W is mirror dual to a final manifold X if the classical period is equal to the regularized quantum period. Okay, so equivalently you can say equivalently you can say that the operator L is the regularized quantum definable operator. Right?
Alex, you have a question in the chat.
Sure, I saw. Not actually. There is no. This not for this W. Not for this W. No, 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 not for this W. This Laurent polynomial, right? I'm not really familiar with that, but of course there is this interpretation in terms of the physics, in terms of consider supersymmetric sigma models. We can take. So the question is about if we can interpret the period of the Landau-Ginzburg model as some sort of Yukawa coupling associated to the potential, right? And so my answer should be like, okay, you can get this. So maybe you made this interpretation. So you can replace the supersymmetric sigma models we had last time by Landau-Ginzburg theories, and that's actually one of the motivation from the physics point of view for the discussion. But I don't see how actually we can talk about the Yukawa couplets in that context or not. Okay, I'm not really sure, and I have to think about it. Okay. Are you happy with my right? Okay, perfect, good. Right, so yeah, because it's right. The question has a lot of sense because it's like the Yukawa coupling was computing Gromov-Witten invariance, in certain sense, right? And of course, there is a relationship between. Okay, this regularization procedure actually relates here. There is some hidden story that there is some relation between the the mirror symmetry for the fan and the Calabi-Yaos, etc. You take, for example, this is that is a course, so I can put this exercise, so you can try to look at this. So not consider CP2, consider CP4, and try to make the discussion for the CP4, and then consider the quintic, right? As a Calabi-Yau hypersurface in CP4, and try to implement this picture for the mirror symmetry for CP4 and the picture we know for the CP for the mirror symmetry for the um, for the quintic by Candelas de la Osa and other people. There should be some compatibility between this picture. This is not. I think there is many folklore results and many folklore statements about that. So far, what I know is kind of sometimes is discuss how is the relation between the Fano, the Calabi-Yau hypersurface, the log Calabi-Yau. I don't talk about log Calabi-Yau here, but there is some log Calabi-Yau there on the canonical bundle of the total space of the total space of the canonical bundle of the Fano, which is actually related also with this regularization. So I think there is a recent paper by Michel Van Garrel and other people, and they discussed the CP2 case in some detail. But for me, I mean, so far is the clear picture is still far from being understood correctly. But maybe you talk with people who are experts, they say, okay, now complete is clear, you have to do this, and this. But if you go to really to fill out the details, you'll be a little bit different. And I guess this should be related with the question by Avanades about if we can have this kind of interpretation in terms of some kind of Yukawa conflict or something like that, right? I think that there will be probably the place to find an answer, right? But that I should think about it, okay? Okay, the periods and the periods of the computer calamity. Yes, exactly. There are some relations. And I can give you, you know, you and the other people some references where this has been discussed, right? Perfect. Okay. So so let me use okay. So let me just continue. Good. Okay. If you want to be more, fancier, let me just in the fancier way. Let me to write this, because it looks smarter. This statement. So this hot theoretic mirror means that the regularized um, quantum cohomology di modo, quantum cohomology di modo of a Fano variety X is identified with the Gauss-Manin connection, the Gauss-Manin connection on the fibers of W. Oh my God. Sorry, WY Z. But of course, you can see, okay, you are kind of cheating us because you talk about Landau-Ginzburg models, some kind of quasi-projective Calabi-Yau, blah, blah, blah. But now then you shift to Laurent polynomials and you make some picture for the mirror symmetry with Laurent polynomials. But how about the Landau-Ginzburg models, right? I mean, the more general Landau-Ginzburg models or something of this type, right? So in fact, actually, we can use the following observations. So let me make this kind of observation. This is a folklore conjecture, uh, but it's kind of written down as folklore conjecture. It is actually written down in this paper by Galkin and Usnik on mutations of potentials. Actually, I will back to this work in the next lecture. Will be actually mutations of potential around polynomials. So this is probably, but this is still there. This observation is in this paper, and also probably in some work by Batirev, Siosian, Fontanine, Kim, Van Straten. Okay, and the observation is the following. So if X is a Fano variety, okay, and X admits a degeneration, somehow in a nice, toric variety to a geometry, a Gorenstein phanotoric variety too. The singularity will be something. If there's a singularity, there is okay because they're Gorenstein, so perfect. So we have you can degenerate. You have this degenerate picture for the Fano to this kind of toric variety. Then the mirror of X admits a chart, which is a torus chart, to which W restricts to a given Laurent polynomial. Then you call it P, whose Newton polytope is the anticanonical polytope of T. So this means that this has been actually verified for complete intersections in toric variety, also for some Fano complete intersections in flag manifolds by Doran and Harder. It's kind of recent work. So Doran and Harder have studied this kind of things, right? So you can find it. There is this particular paper. I have here the paper. So toric degenerations. You can look at this paper. Toric degenerations. And Laurent polynomials. Related to given tals Landau-Ginzburg models. So you look at this paper by Doran and Harder, and also you look at the paper by Doran. I think Harder is still Prichalkovsky and Katsarkov, and they study modularity of Landau-Ginzburg models. So there is also this paper, modularity of Landau-Ginzburg models. This is by I guess Harder is also an author of this paper, but certainly Doran, Katsarkov, Prichalkovsky. So you can find this picture somehow in these two places, right? So the idea is essentially using this folklore conjecture, this statement that okay, if you have Fano and we expect that all Fano has this nice degeneration, so you have this degeneration to the historic variety. So you can, in the mirror side, this means that you can restrict to just to consider the mirror in one chart, and in that chart we have a Laurent polynomial. So the picture, so if you have this mirror picture for the Laurent polynomial will be enough to consider the Fano. That's actually the idea we will use, right? So one of the interesting questions is that okay, is this Laurent polynomial unique? For example, for the CP2, I get this x, for CP2, we get x plus y plus 1 over xy. So question, so is the Laurent polynomial unique? Laurent polynomial unique. And maybe you see, it depends on what torus chart you are, but you change the torus chart, so you change the Laurent polynomial. The answer is yes, it's not unique. So not unique. And in study how this actually change, what is the relation between the different Laurent polynomial when we move to different torus charts, we need the notion, we need the idea, the notion of mutations. And that's it, the lecture 3. So the first lecture next week on Monday is mutations potential. So I will discuss this problem, how actually the Laurent polynomials behave under the mutations, right? So somehow using these mutations things, so we now have a better characterization of the classification program, because now you can invert the problem and say, okay, classify, if you get the Fanos, so you get the Landau-Ginzburg model, the Laurent polynomials, so it's expected that is a way to construct a family of Fanos associated to these Laurent polynomials, and then you find the way to classify the Laurent polynomials, which potentially are mirrored to Fanos, so you get the classification of the Fanos. So that's the Corti Galkin Golichev Kapschik program. So they want to classify Fanos by classifying the mirrors, because if you can classify the mirrors, you can classify the Fanos. So you can naturally ask, okay, it's easier to classify the Fanos, to classify the mirrors than classify the Fanos? I don't know, maybe not. So far, they only reconstruct the classification in dimension 2 and dimension 3, but this is a little bit easy in the sense we already know the answer, so we know what to get. But for the dimension 4 and other dimensions, I think there is no, strong results or something like that. But still, you can think of mirror symmetry for in order to consider this classification problem. Good. So I have 5 minutes probably. So let me just mention in this 5 minutes something very short about homological mirror symmetry for Fanos, which I think is kind of interesting. So let me conclude with this homological mirror symmetry for Fanos. So again, remember that we have the A model, which is kind of symplectic psi, and the V model, which is the complex psi. So in the Calabi-Yau situation we discussed last time, we have two categories, right? The category of coherent chief and the Fukaya category, and so there was this relationship between the categories. Now we don't have, in one side we don't have a variety, so we have this variety with a potential. So we need some modification for the categories here. So if you consider the final X as an A model, still you can have the Fukaya category or the derived Fukaya category, so you can define the Fukaya category, is okay. But now there will be equivalent to certain category associated to the Landau-Ginzburg model, which is this category singularities. So this thing is the category of singularities. Singularities, right? So this is actually, in this paper by Orlov, I mentioned last time, Landau-Ginzburg model, Orlov, right? In his paper, Landau-Ginzburg models, B-branes, and mirror symmetry, you can find the definition of this category. The singularity category is actually, he actually defined the category of matrix factorizations, and he proved that this matrix factorization actually coincides with the category singularity, so you can find it over there, right? And the other thing is like, okay, if you consider the Landau-Ginzburg model as the A model, it's kind of symplectic object. So you don't have the Fukaya category, but you have some modification of the category, which is the Fukaya-Seidel category. Fukaya-Seidel category. It's kind of modification of this category, the Fukaya category given by Seidel, right? And then this should be the derived category of coherent chief of X. That will be the mirror, the homological mirror symmetry for Calabi for fun. I want to say something very interesting in the proof of. Let me sketch Seidel's proof homological mirror symmetry for CP2. So remember that we have for CP2, we have this mirror, no? The mirror of CP2 should be something like x plus y plus 1 over x or something like that, right? So this is actually this Landau-Ginzburg, this Laurent polynomial interpretation of the given tal mirror, which is some hypersurface and with some potential, right? What was interesting was the following. So Seidel actually proved the following. So Seidel proved that if you consider the Fukaya-Seidel category of Y, this is actually equivalent to the derived category of representations of some quiver. Let me call it B, right? So B is a quiver. What is a quiver? It's an oriented graph. In this case, actually, these 3 points. And there is some arrows here between them. Representation of a quiver is used to put complex vector space on the vertices and linear transformations in the arrows. So this relation means that Bi, there is some relation Bi Aj are equal to Bj Aj, I minus J, and Bi Ai are equal to 0. So Seidel proved that this Fukaya-Seidel category for this potential here, this will be this YW, is the direct category representation of this quiver. But it was known by Beilinson. So on the other hand, in the 80s, Beilinson proved or showed that the direct category of coherent shifts of P2 is exactly the direct category of representations of B. Actually, B is because the quiver is called Beilinson quiver. So then, we had the Fukaya-Seidel of it's equivalent to the direct category of coherent shift P2. It's very interesting because there is, this, relationship with the direct category for the representation of quivers, which is actually very important in mathematics and physics nowadays. So there are quivers everywhere in discussing mirror symmetry from the mathematical point of view right now. So this is and I like because this proof is from probably 2000 or something like that, right? Seidel did this proof. But I like it because it relates actually with this quiver and with the representation theory, which is really it's quite nice thing. So I probably will say something at the end of these lectures about somehow this quiver point of view, right? This relation with the quivers and this kind of thing actually leads to another important subject, which is actually called the Dubrovin conjecture. I won't say anything about the Dubrovin conjecture during these lectures, but I have to say that I have been working a lot for the last 15 years in Dubrovin conjecture. So you look at some of my papers in archives, you can find it. So and that's Dubrovin conjecture is a kind of very nice thing because it is a manifestation of this homological mirror symmetry philosophy that the triangulated categories are related with these non-commutative hash structures. So I like Dubrovin conjecture in that sense because it gives an idea of how this geometric picture using categories, certain type of categories actually fits with this kind of extension of the hash theory in the non-commutative world. Okay, so I think I can stop for today. So if there is some questions or comment, please.
Sí. Thank you, Alexander. So let me stop the recording so people can ask in a more relaxed way. Wait, is